So does she spend the next year kind of analyzing the data, coming out
Well,
with
she's
best
already
practices?
started doing that.
Oh,
She's got a
okay.
publication under her belt and
Oh,
another
nice.
one in review. So she's already been doing it as she goes. So the parts of it are done. The other parts of it, I like them to like publish, even if it's like if you go publishing conference papers, you get the feedback and then you turn those into journal papers. So she's been doing that, and so otherwise the writing stays till the end, and that's never good.
I agree.
So
Work
you
on
write something every
something
6 months. If you write something every
or
6 months,
TRB.
yeah, she got some really good reviews from TRB actually. So, and then with this data collection, that TRB paper is going to turn into a journal paper.
Journal paper.
Yeah.
Was it accepted then? So she'll be presenting there?
No. TRB, we just put it in for a presentation only. So it'll be.
So like a poster session?
Yeah. No.
Oh, you wanted a lectern?
Lectern, yeah.
There's like not as many this year.
Well, we still got a lectern. Lectern, and of course she'll do a poster too. So.
Oh, that's good, because yeah, the subcommittee I'm in charge of, we couldn't do any lecterns. Normally we can always get a lectern session, but they've eliminated.
We got our lectern session. Everybody loves
it.
it.
Yeah, because you're full committee.
Yeah.
They limited the section lectern session. Okay. There was 2 additional each section we could have, and that was how our subcommittee got them. So each committee got 1 lectern session.
Nice. Before we're getting close to the time here, so I'm going to quickly ask Sue a question. Sue, we're going to, within the very, very first few minutes, we're going to do our 2 truths and a lie thing. And so will you bring that up, or?
When you pull up your slides online, that will be the trigger for Sue to launch that.
Sounds good.
And,
actually, yeah.
And I'll start here in just a minute or so with the background, welcome here. We're almost to that time.
Do you want me to share my screen, Audra, or just?
Shortly, I'm going to share some slides first, and then I'll let you share your screen.
Sounds good.
Yeah. Yeah, in fact, I have it's time to go. We get to start with the soft introduction so we can make sure our online is right on time. It's at 6 o'clock. So good evening, welcome, and thank you for tuning into Husky Bites. If you are a return visitor, we're so glad to have you back. If this is your first time to attend Husky Bites, welcome, and I know you're in for a treat tonight. My name is Audra Morse, and I'm the chair of the Civil, Environmental, and Geospatial Engineering Department. And I have a few just updates and things that I get to share with you. And the best part is that I get to do a promotion for the department. So as the Civil, Environmental, and Geospatial Engineering Department, we have 4 undergraduate degrees. 3 are primarily in the department: Bachelor of Science in Civil, Bachelor of Science in Environmental, a Bachelor of Science in Geospatial Engineering. And if you're a Husky, you might remember that as the surveying or surveying engineering degree, but has been rebranded as Geospatial. We have a really good reason for that, and is now home. Its home is the Civil, Environmental, and Geospatial Engineering Department. We also support the Construction Management Program. That program is co-administered by this department and the College of Business, which is something that makes the construction management program unique. Besides the undergraduate degree programs, we have several graduate degrees. We have accelerated degrees, which are for our own students, so that they can, quickly either do coursework or master's, and can seamlessly go from their undergrad to a master's degree. So we have civil and environmental engineering and environmental engineering science degree. We have the integrated geospatial technology degree. What's special about that degree is that it has been and continues to be both on ground and fully online. And then we have a PhD in civil engineering and a master's or a PhD in environmental engineering. But one of the things we've done in the last 2 years was to add certificates. And these certificates can be combined and then work towards a master's degree. And the certificates are a function of the expertise that we have in the department. And many of these are online, including advanced photogrammetry and mapping with UASs, geospatial data science and technology, We have a resilient water infrastructure, several in structural engineering, so that as you build those together, you work towards your master's degree. And we have a water resources modeling. These certificates we generally launch in like September. In January, you can take 1 class, 2 classes, or more. We have students that have completed a master's degree and certificates along the way, and you can do all that in as minimum as 3 semesters. So if you're thinking about continuing your education or want to study with exciting faculty such as Amlan Mukherjee, who you will hear from shortly. And what's been great is you've heard from several other faculty members this fall. We've been prominently displayed in the lineup. Think about one of these, either master's degrees or certificates. So tonight's Husky Bites is sponsored by the Civil, Environmental, and Geospatial Engineering Department. And as you know, if you've tuned in every week, you're familiar with the format. We'll start here in just about 2 minutes. Amlan will share some words of wisdom with us, and then we'll have some time for Q&A at the end. We are live. Last week was exciting because Facebook was down, but not this week. We are live here tonight on Husky Bites, so you can follow us there, or know that this is recorded and will be shared on the Husky Bites website at Michigan Tech. Now, what's coming up? Tonight, we're NetZero. How do we get there? With Amlan Mukherjee and co-host Heather Dylla. And then next week is the tiny house design, weather, watts, and materials. The speaker is Paul Sanders, but I can't help but brag that the co-host is Sierra Braun, who is a 2021 civil engineering student. And so I'm excited about that. And I hope you will tune in next week. And I promise you, Janet will be back. At least I'm pretty sure Janet will be back. And I'm happy to turn the reins back over to her. So we do like to ask who's joining us today. Pick one best answer that represents who you are. Are you a Michigan Tech student, a pre-college student? Maybe you're attending with your family. Maybe you attended Michigan Tech faculty, staff, friends of Michigan Tech, family of current or future students. Maybe you're a K12 educator, or you're just a curious person. I personally like number 8. And let's see, who do we have with us tonight? We have, let's see, about 79% are alums of the university, and I bet probably the College of Engineering, so we're really glad to have you back. We have 13% Michigan Tech, 13% Michigan Tech students. We have a few friends of faculty and staff who are attending us, some friends of Michigan Tech, and then family of current or future students, and some K12 educators. So thank you for being with us tonight. All right, and I'm going to go ahead and share those results. Let's see, for those K12 educators, just a quick reminder, if you're a K12 teacher counselor in Michigan, you can participate as a Husky Bites professional learner this fall. You need to attend a live session on Zoom, and you can earn 1 Schechech, SCHECH per session. And you can become a professional learning community member and focus on sustainability engineering and design, and you can earn 9 of those Schecheches this way. So there, I think you needed to sign up by last week for this fall, but if you'd like to learn more, please check out Husky Bites or send questions to engineering@mtu.edu. So again, next week, we have Paul Sanders, who will be talking about the tiny house project. And Paul Sanders is in the materials science engineering department. And so I know it's going to be exciting, especially because Sierra Braun is going to be there as well. So I'm going to stop now and let Amlan share his screen. I know that Amlan has given her kind of an honorary Husky membership because of their collaborations over the years. So Heather, thanks for joining us tonight.
Thank you. And I get the pleasure to introduce my mentor, colleague, and friend, Dr. Amlan Mukherjee, who's a professor in civil, environmental, and geospatial engineering. As you all know, I met Amlan first at the National Asphalt Pavement Association when I worked with them, and we worked together trying to understand how pavement, particularly smoothness, interacts with the vehicle fuel economy. That led to bringing him on to sabbatical. I thought it was pretty cool to have a mentor come and work for me with the association on sabbatical. And he helped me really forefront the environmental product declaration program, EPD program for the asphalt industry. And these are like labels that for products such as asphalt mixtures, declaring what is the environmental footprint. And that was the first in the nation for asphalt mixtures, and was an international standard that was later adopted in Australia. So I think that was a great accomplishment there for our work. And then later went to FHWA to lead the Sustainable Payments Program Technical Working Group, where Amlan actually, he was there before I was as a technical working group member. So he has actually been a member of the Technical Working Group for Sustainable Payments at FHWA longer than I was. However, Amlan joined FHWA recently. Our trend continues on sabbatical. Shortly after, Amlan predicted that I would leave, and sure enough, that is the trend. But I'm so proud that Amlan is at FHWA to lead the sustainability efforts there, particularly in asset management. So he'll be building out and providing recommendations for state DOTs. So with that, I'm excited to hear the presentation, Amlan. I'm going to turn it over to you for you to give a little discussion on pathways to net zero.
Thank you very much for all those wonderful introductions and very kind words. It has been an absolute pleasure working within the Sustainable Payments Technical Working Group, and of course with Heather. As is known in our professional community, Heather and I often have disagreements, but always good things come out of the disagreements. And if you ever get caught in one of our professional fights, it's not funny. But then it's been a very creative tension, and we've managed to have a lot of fun at work, which, if you can have fun at work, hey, you don't work a day in your life. So that's, and I'm very blessed that way. So today we're going to talk a little bit about pathways to net zero, right? And how net zero is a way, or is being considered one of the tools in our toolbox for responding to anthropogenic climate change, right? And that's a little bit of a big word, but we'll tackle that shortly. But before we start off, I got this picture from one of my former PhD students, Chris Van Arstel. This is the picture of Agate Street in Houghton on the morning of the Father's Day flood, which was 3 years ago at this point, right? And if you look, this is an asphalt pavement, and as you see, it was completely washed out. The foundation was washed out. There was pretty much no pavement left at that point. And I have to say, that morning, people walked around it, and in some situations tried to drive around when they shouldn't have. But it was quite an eye-opening experience, right? And what we've been seeing in the last few years is increasingly we're seeing extreme weather events like this. And of course, extreme weather events happen from time to time. They're not uncommon. We refer to them as 100-year floods and so on. But what we're seeing is that these extreme weather events are happening more and more often, right? They're happening more and more often, and each time the extreme nature of it is, and the impacts thereby.
Amlan, can I pause you for a second?
Sure.
Speak up a little louder.
Okay, thank you, Heather. So the impacts thereof, whether it be in terms of cost or whether it be in terms of human lives, are going up, right? And so part of this is, we're looking at our underlying models, the models, climate models, the work that has been going on. In fact, the Nobel laureate in physics this year, one of the arguments that the Nobel Committee presented was that his work on complexity helped us understand some of the climate models and the predictions of the climate models. And what we're seeing from them is that anthropogenic climate change, i.e. climate change caused by human beings, due to carbon and greenhouse gas emissions, are leading to a lot of these, get the arrows right here, are leading to a lot of these extreme events. And so the question is, what do we do? How do we handle that, right? So before we go on, we're going to quickly go ahead and with one of these 2 truths and a lie. And to be sure, we're not really good liars. So they're really truths. They're just sometimes a softer truth, right? So which one of these do you think is a lie, or well, a not full truth? Heather, do you want to jump in?
Read out.
Yeah,
So the first option would be A. Since the beginning of the industrial age, concentration of carbon dioxide in the Earth's atmosphere has increased 47%. Your second option is B, which is the current climate change is part of a natural phenomenon due to the increases in solar radiation and the Earth wobbling on its axis. And then the third option would be C. Without greenhouse gases, the Earth's average temperature would be approximately negative 19 degrees Celsius. So right now I'm looking at the poll, and about 56, 55, 57% is wobbling a little bit, is around B. So the majority of you all believe that B is the lie. But there's a good tie between A and C, with around 20% for both A and C. So Amlan, could you enlighten us a little bit more?
Yeah, sure. So we wanted to address this because, again, as I said, there are truths and there are soft truths. And so strictly speaking, if you look at where and why we use the term anthropogenic climate change, is that the warming tendencies within the Earth's climate, and really in the lower atmosphere that we're seeing, is happening over a very short time period. So this is happening over the last 200 years post-industrial revolution. And so really in a matter of centuries, in the order of time scales of centuries and really decades, as we're seeing in the past 20 years, our carbon dioxide has gone up 11%. And really, in the last, since the industrial age, it's gone up to 412 actually. So the statistics on this slides are directly from NASA's webpage. And so it's 416 as of this morning, 416 parts per million. And parts per million sounds like a very small amount, but that's actually a fairly significant number in terms of the effect it has on heating the atmosphere, right? And so then you say, well, but isn't this so sure as a result there you're having the polar ice caps which are melting, and then the more greenhouse gas in the atmosphere, the more heat it traps. So generally speaking, having greenhouse gases is a good idea because, as we noted, one of the outcomes is that if we didn't have greenhouse gases, if they weren't creating a warming environment or a warming effect, we would be at minus 19 degrees Celsius, which, well, even for those of us who live up in Houghton, it's not a very comfortable temperature, right? It's not very, so, and that's an average temperature we're looking at. So our average temperature, the Earth's average temperature is around about 14 degrees Celsius, right? And so what we've been seeing is this temperature rise by 1.18 degrees Celsius. And what we're trying to avoid right now is that 1.5 degrees Celsius mark. And then you say, well, 1.5 C is not such a big deal. It's just 1 degree. And, on an average day, you won't even feel that difference. But we're talking about the global average, right? So if you think about the extremes of temperature in the world right now, the lowest temperatures we get up in the poles versus the highest temperatures we get up in the middle of the deserts. So you realize that given that range, 1.5 is actually quite significant, and it translates to that much amount of energy in the atmosphere, which what we're seeing in terms of these extreme weather events, right? And so on the one hand, yes, we want our greenhouse gases. They're good for us. They keep us warm, but we don't want them to keep us too warm, right? So then the question is, well, what about the other option, our quote unquote lie? So is it true that the climate change is not part of a natural phenomena at all? And then that's not, again, we know for a fact that these cycles do happen, and the Earth's climate has changed multiple times. But what's crucial to note out here is the timescales over which these natural climatic changes happen, right? So for example, yes.
Speak louder and maybe a little slower. You tend to be a little bit quiet and you speed up. So
okay, thank you.
Yeah, just project.
Okay,
I'm trying to yell in my. hopefully.
Okay. So I was saying that with the orbital cycles, the idea that, as the Earth moves around or quote unquote wobbles on its axis or changes its orbit, the shape of its orbit, would that, change, have an effect on the climate? And it does. But the timescales are over tens of thousands of years, or in some cases, hundreds of thousands of years, right? So this is kind of important. So you're looking at between 26,000 year change and 100,000 year change and 41,000 year change, right? And this is important because when the changes happen over slower periods of time, life on the planet actually tends to adapt and evolve accordingly, right? When we are, and the same thing with the other plot that you have on the right-hand side of the slide, you're looking at the influx from the solar energy, the solar cycles, right? And we're clearly seeing that this is not directly correlated with the temperature changes and that we're finding because of the anthropogenic climate change, and which is the component because of carbon emissions and greenhouse gas emissions that have gone up due to our industrial activities. Right. So talking about that, I've kind of said carbon emissions and I've said greenhouse gas emissions. So now it might be a little time to explore that a little bit one more time. And let's try these three here.
Before you do that, Amlan, go back and re-highlight what was the lie of the last one.
Oh, yes. And in case I didn't, the specific lie of it was that when you talk about climate change, when we talk about response to climate change, right, we really should be focusing on our response to anthropogenic climate change, which is the carbon emissions, and as we're discussing in this next poll, carbon emissions, greenhouse gas emissions that are actually throwing the net warming in the atmosphere over what is comfortable for us, right, and for life on this planet. That is not to say that climate change, again, as we said, this was the soft lie, not to say that climate change doesn't happen because of these other reasons, but these reasons are not what is causing this warming right now. And that is pretty conclusive. So when you hear people, if you come across information that says that, well, climate change is natural and it happens, and you say, well, it does, but the climate change, that these natural cycles that we're talking about happen over hundreds of thousands of years. And that is not what we need to worry about. In fact, if we were within that cycle, we would at this point be cooling because of where the Earth's orbit is right now. And same thing with the sun. If you look at the solar energy coming in, there has been not a direct correlation between that. Meanwhile, look, we have our...
yeah, why don't you go back to the other slide with the poll?
Yeah, I'm going to go back to the next slide. Thanks, Heather.
So again, 2 truths and a lie. A, greenhouse gases include CO2, carbon dioxide, water vapor, methane, nitrogen oxide, sulfur oxides. Or B, reducing greenhouse gas emissions will help mitigate anthropogenic climate change. Or C, global warming potential is measured in CO2. And this one, the majority is with answer C. And then second place would be B, reducing greenhouse gas emissions. And then the last one would be A, with the least percent. But 63% believe C is the lie there. So Amlan, what would you say?
Yeah, and I think we have that is absolutely correct. C is the quote unquote lie again, because remember, it's the greenhouse gases that cause the warming, and so it's not just carbon dioxide, but it's all the other gases that we have listed out here: water vapor, methane, nitrogen oxide, sulfur oxides, and there are a few more on that list. But generally speaking, what we use is a term called global warming potential, and what it does is it looks at the warming effects of each of these gases and multiplies it by an impact factor, right? And so, for example, carbon dioxide has a warming potential of 1, and everything else is measured as a relative impact factor with respect to carbon dioxide. So methane, I think, is 24, right, Heather? And so on, right? So if you have 1 kilogram of methane in the atmosphere, it has 24 times as much warming potential than carbon dioxide does. So what we do then is we add all that stuff up and we express everything in terms of carbon dioxide equivalence, okay? Carbon dioxide equivalence that we refer to as the global warming potential of a particular product or a process based on what the emissions are. So if you have 1 a kilogram of carbon dioxide that is emitted from a process, and 1 kilogram of methane that is emitted from a process, then your net global warming potential in that case will be 25 kilograms of carbon dioxide equivalents, right? And that's kind of important to remember, because this entire conversation, and the reason we're having this discussion, is the entire there is a question there, and we'll take that question in a second. The reason we're having this discussion is that ultimately, if our attempt at dealing with anthropogenic climate change is to reduce the greenhouse gas emissions, to maintain that temperature rise, to limit it to 1.5 degrees C. And in order to do that, we have to have a measure for that, and measure is global warming potential. Now, through the rest of this presentation, if I'm using carbon dioxide, I always mean carbon dioxide equivalents, okay? And if I say greenhouse gas emissions, I'm talking about all of them. And then so all our methods are based on this life cycle accounting. And even when we talk about carbon accounting, or if you hear somebody talking about carbon accounting, make sure you check. We're talking about carbon dioxide equivalents, right? Because it's not just enough to talk about the carbon dioxide. We must also know the impacts of the other greenhouse gases, which also have a significant warming effect. So talking about,
I was going to say, I think that's an important thing to highlight, because I have reviewed in the federal highways many documents on strategies, and they won't include the equivalents. And it's so important to know whether it's CO2 equivalents or is it CO2 that you're only speaking about. So I think that's good that you've made that clear. It's easy to forget, but in this presentation, we're only talking about CO2 equivalents.
Right. And we have a comment from Robert Anderson saying temperature change seems to be much more noticeable in the higher altitudes like Quito, Ecuador. Of course, the fact that Quito has changed from a population of 1 million to almost 3 million since 1965, and that's the other thing, and we'll talk a little bit about how these are affecting different populations in different parts of the planet differently. So on that note, if we start thinking about carbon accounting, right? So how do we measure carbon? What do we mean by saying, let's make an estimate of what the quote unquote greenhouse gas emissions or the global warming potential is of a product or a process? And again, as engineers, we think in terms of products and processes. So for example, it could be this coffee mug, right? Or for the area that Heather and I work in, we think in terms of our infrastructure, our civil infrastructure, our pavements. But the underlying processes, the underlying the science is very much the same. And what we do is we start off by looking at where all the raw materials came from, and these raw materials typically come from, as it's either mined or it's grown, so they're coming from earth-based systems, right? So where are the raw materials coming from, and in the process of extraction of those raw materials, where are the carbon dioxide, again, carbon dioxide equivalents that are emitted, same thing. And then what happens with the design? What kind of so for us, when we design a pavement, are we designing a pavement for a highway? Heavy traffic, or is it something like our 7th Avenue right in front of a residential street? What is the nature of the design? The nature of the design impacts the methods of construction, which in turn impacts the entire emissions associated with that, what we call the life cycle stage, right? So then there's the production, manufacture of the materials that come in, right? So when Heather mentioned that we'd worked on the environmental product declaration program for the asphalt mixtures, what we were doing was essentially making this estimate and saying, for 1 short ton of asphalt at the point when it leaves the plant, what is the total life cycle greenhouse gas emissions measured in global warming potential that we can put a number to it? And the number roughly is between 55 and 60 per short ton of asphalt mixture, right? And it varies depending on your design, because you could have more recycled materials in it. You might have more reclaimed asphalt pavements or ground tire rubber, or you might have a modified binder, and that changes that number, right? And that's part of how your design choices make a difference. And then of course things have to be moved, right? Everything moves around, whether it gets shipped, whether it moves on a barge, whether it's on wheels. So all of that, transportation has a major contribution to our emissions, right? And so when you're thinking about food and you say, well, I want to eat more local food, yeah, you might want to think about that a little bit, because remember, the biggest impact, the transportation impact for your food is the last mile, where you're the only person probably in your car driving your food back home, versus the big truck that brought in a lot of food for over a longer distance, right? So these ratios of functionality, like what is better, what is where are we getting more bang for our buck for the energy we are spending, for the emissions that we're producing, right? What is the functionality? All of that comes into this methodology. And then of course we get to the consumption phase, right? And the consumption phase is typically the phase that has the highest impacts, right? And the highest energy use. And this is a very interesting phase. And when we get to the end of this conversation, we'll spend a little bit more time talking about what we can do. What is our role? Because we are, well, we embody the consumption phase, right? Our choices impact that carbon dioxide emission. So when we put together a highway, well, we put together a highway and we can tell you, make estimates up to the construction and the opening of the highway, right? Well, what happens then? All of us get to use the highway, and the more we use it, the more those emissions get associated with the use phase of that particular highway. And then if we build it well, if we design it well, it lasts for a longer time. That means that we're getting a little win because we have fewer maintenance and rehabilitation operations. If we do a poor job constructing it, well, guess what? We have to go back and do more of those maintenance and rehabilitation operations, and that adds up to the emissions, right? So we want to do these optimization problems a little bit. So all of this kind of sums up, and then of course there's the recycle. Before I move on to the summing up, there's a recycle and the reuse. So we're moving towards something we're increasingly referring to as a circular economy. Is that what happens if we don't create any waste? What happens if all the materials we're using can continue, and the resources, not just the materials, the resources, we can keep continuing to use in different ways. We can reuse, we can upcycle, we can downcycle, we can recycle, and there's a whole set of terminology out there we could spend at least an hour talking about. But the idea is that how do you make sure that these resources are not getting wasted, that have already have come out of the earth, either mined or mined, extracted, and or grown, right? So now if you look at a particular product or a process, right, you sum up all the emissions over all these life cycle stages and say, well, that's my total life cycle emissions, and we sum up energy and we sum up the greenhouse gas emissions as well. And then I'm not going to go into energy today. I'm going to focus only on net zero emissions, okay? And then we say, well, now what? How do we get into an accounting that takes us to net zero? Because ideally, we'd like to have these processes to essentially have a net zero emission impact, right? How does that happen? So you say, well, let's start off by saying this is our total life cycle emissions. Okay, now we can make some decisions, right? And this is, we can start off by saying, well, we can re-engineer a product. Like with asphalt mixtures, we can say, well, we can use more reclaimed asphalt pavement. We can use more recycled materials, right? We can, when we're making a concrete mixture, we can remove some. We can replace some of the cement with other cementitious materials like fly ash or slag that come from other industrial processes, right? Well, that's great. That reduces the impact. That does reduce the impact quite a bit. So when we are doing this, we can say, well, how do we re-engineer a process? Where can we use recycled materials without compromising the functionality of the product or the process? How do we re-engineer it to reduce some of those life cycle emissions, right? And then once we've done that, we say, okay, now let's figure out an accounting by which we can start coming up with negative emissions, so that when we add them to our positive emissions we've racked up, we get a net zero. Well, one technology, or an area of technology that's been picking up steam is carbon sequestration, biogenic uptakes, and we'll be getting into that accounting in a second here. The other is doing carbon dioxide offsets, and you may have heard some of this too, and we'll be primarily discussing these two ways of finding these negative emissions to get ourselves to net zero, right? There is another approach called avoided burdens, and but we won't get too much into the detail of that because it takes us a little bit more into life cycle assessment based methods. But I think we'll cover some of these, and the goal is that we are in the next 10 years. There is and Heather, correct me on this one, right? There is a 10-year goal. Amazon has signed on to the 10-year goal for to get all their processes to net zero. Amazon.
I don't know about Amazon, but I know that there's a 2030 goal and there's a 2050 goal. 2050 is net zero for sure. Then beyond that, it goes beyond. We have to get beyond net zero, but 2050 net zero, 2030 is definitely I think it's 50% reductions.
Right. And there are, Heather, do you want to quickly jump in terms of some of the policy stuff that's happening across the country in terms of that little re-engineer, reduce component with EPDs?
Yes, so we're getting to a stage, many of us probably recycle or, will look at different, there's different practices we do and we don't think about them. They're more of norms, or what I would call feel good. And recycling in the paving industry is definitely one of them. It's been done, a lot of it has been done for the economic savings that they do get, but we haven't really quantified the environmental impacts of that to know, is it really actually more environmentally friendly as well? So there is a movement to start quantifying the environmental footprint of various design decisions. It can be of recycling, but it can be for any product, as Amlan mentioned, and states are requiring what labels called environmental product declarations for purchasing public goods. And one is asphalt mixtures, for example. So in my new role at Construction Partners Incorporated, we'll likely be looking at how to get EPDs for our mixtures and plants so that we have these labels in place for when the state DOTs start asking and specifying them. There's many ways to incentive that reduction that you see there, whether it's you put a product threshold. That's what California is doing. So all concrete with a certain mixture has to be, if you're going to purchase it, they're going to start setting thresholds and they have to be lower. They're continually moving that bar down. Others may look at it from a project level and look at, well, maybe not by specific product, but the construction manager and the designers can put together what technologies they think are going to get to be lower than this project threshold. So there's various incentive techniques being explored. California is the first one to advance in this that's in law. Colorado has followed, Oregon, Washington, all looking at similar legislation, Minnesota, New York, all very similar. And then federally, there's also some language introduced following similar techniques.
Yeah, thank you. So moving on, let's just take a look at some of these pathways, pathways to reducing, pathways to net zero. And so the first one is reducing emissions. Well, how do we reduce emissions? And there is the easiest one, which is, well, that's the red arrow right there. That's your big total life cycle emissions. Where is much of our energy still coming from? It's fossil, or when there is a process where you have fossil-based energy. Well, there is one thing you can do. You can start using renewable energy. Now, as we go through this discussion, I want to point out that pretty much all the things that I'm talking about out here, none of them are solved problems. They all have concerns and issues, and there are plenty of engineering challenges that we're still working through. Renewable energy is great, but at the same time, the fossil fuels also provide a very efficient source of energy. So the question is, will we turn off fossil fuels overnight? Probably not. So how do you create more diverse energy portfolios where, in some cases, for example, where we have on-site generation possible of renewable energy, right? And we're seeing some of this in the construction materials industry. We're seeing the use of synthetic natural gas. We're seeing the use of fuels that are coming from, and I'll talk about that in the next slide, but we're seeing a variety of different fuels, many of them renewable, many of them coming from upstream use of other products, or they're big, used cooking oil is a source of energy that is being used. So there are ways to look at our energy and say, well, even if we don't go to 100% renewable, there are ways in which we can reduce our fossil fuel-based dependence, and that in itself can create significant reductions. In the buildings industry right now, where if you're looking at an existing building, if your entire energy is coming from hydro, and there are parts of Vancouver, Washington, where hydropower is significant, you could argue, and at least there are some buildings organizations that are making the argument that the building is net zero because they're getting all their electricity and energy from a source that does not produce any carbon dioxide or any associated greenhouse gases. And that's not entirely correct, because there are transmission losses, there are line losses, all that stuff, but it does significantly reduce the impact, right? And on that, let's do a quick little talking about renewable energy. Let's do a quick little two truths and a lie on this one. Actually, this one actually has a flat out lie.
This is energy.
There is nothing soft on this one. This is a flat out lie.
in 2020. Your option is A, conventional hydroelectricity generation was about 7.3% of the total US utility scale electricity generation. B, the US leads the world in the amount of geothermal electricity generation at 0.4% of the total US utility scale electricity generation. And C, coal contributes to 30% of the total US energy consumption. And the overwhelming response is going for B with 72%. Hopefully I'm not influencing your choices there, guys, but.
Well, let's go ahead and end that poll and tell us
Well,
the
yeah,
answer.
so I guess we totally punked you on this one because the lie out here is C. The good news is in 2020, just a smidge less than 10% was the total coal-based consumption. Coal is again, our dependence on coal as a source has been reducing significantly, and that's it has a very significant impact. And so B is actually true. And honestly, when I read that, I was surprised. I was like, this is a good one. We got to put this down there. So yeah, B is true. And yes, conventional hydroelectricity, you're looking at 7.3%. That is also true, primarily in states, in the western states. You're seeing this in California, Washington, Oregon. Those are the states that primarily are using hydroelectricity. And that makes a big difference because that's one way of reducing that big red arrow there, okay? So that was great. I think this one worked. So going on, oops, to the next slide here. How do I pull this off? Yeah. So let's now start expanding that. So we're trying to get this net emissions. What are other ways we can get net emissions? So we can look at our choice of materials. So there's renewable energy, of course, but if you kind of start expanding that equation a little bit and take more things out of the other emissions cloud, right? We can change our choice of materials. We can choose materials that have lower embodied carbon, right? That means that take less energy to produce in the first place. We can use more recycled materials. Lean engineering. We can look at our process design and develop our processes in such a way that we're using less energy. So we published a guide on sustainable highway construction practices. What can we do when we are constructing our highways to reduce or to be more sustainable in the long run? And that's one way, how do you reduce the emissions during these different construction phases, right? So these are all different methods of saying, well, net emissions reduction. We still haven't gotten to negative emissions yet, but it's important to reduce that amount. And strictly speaking, as Heather pointed out, with where the legislation is going right now, we still have a lot of low-hanging fruit in being able to achieve those emission reductions. And again, I'm very proud to say the construction industry has been working on this for the last 10, 15 years. And we've gotten to a point where despite the policy or wherever the policy is, most industries have adopted methods that are actually reducing emissions. And the corollary to that is it's reducing their energy use, which in turn is directly transferring into profits, right? So this is a win-win situation for us right now. And there is a general move towards practices that are more sustainable, that are more and are emphasizing the reduction of greenhouse gas emissions as well as more energy efficient, okay? Now we get to a little bit more of an interesting part. We say, well, how do we get some negative emissions into this equation, right? So we say, well, let's think about using bio-based materials, right? So for example, if you're using a fuel that comes from soy or corn, or as the case may be, right? Well, when you're growing that plant, right? When you're growing that plant, this is referred to as biogenic uptake. When you're growing that plant, it takes in a fair amount of carbon dioxide, right? Because plants breathe in carbon dioxide, unlike us. And so that carbon dioxide is actually coming from the atmosphere and being directly, for all intents and purposes, being removed from the atmosphere, right? Well, that's good. So, well, what if we start using more biogenic products or fuels that are capturing this carbon? So this is right now, as I said, most of these pathways in net zero are still areas of research. So for example, we can measure some of the carbon dioxide that gets taken up when, for example, when you're growing soy, which then gets converted into a fuel. Well, that's great, but once you're converting that into a fuel, how much of that carbon dioxide is going back when you're combusting it as a fuel, right? Besides, remember, we spoke about greenhouse gas emissions, right? So sure, soy does take up carbon dioxide, but it also tends to give out nitrogen oxides during the agriculture process. that balancing is difficult, and there is some research going on, and I know the Department of Agriculture is coming out with a guideline on how to best do this accounting. But this is one way. Now, there are other ways. For example, the asphalt binder, right? The asphalt binder is a vertical tar bottom in the petroleum refining process. Well, when you take that, literally that dark gunk at the bottom of the refining column, and you put it on a pavement, it stays there. That carbon never gets combusted and does not go back into the atmosphere. And so that's a portion of that crude oil refining process where the carbon goes back into the ground, right? And so there are these different ways of accounting for when we use biogenic or materials or more bio-based materials, where we say, well, this material in its production process, instead of just creating emissions, has actually taken up some of these emissions, and maybe we can start subtracting that from our equation. Next one is even more fun, and this is something that you will hear a lot of major corporations doing. They'll say, well, you know what, we're just going to go pay some money and have reforestation of areas in the world. And because when we reforest, and I think there was a question out there talking about trees, and when we reforest, trees, deforestation has been a major problem. But when we reforest large swaths of land, we are in a position to again be able to take in that much carbon dioxide, right? So this is again a way of capturing the carbon back. And then there are some carbon capture technologies, right? So, and I'll talk about carbon capture technologies in a little bit, but there are carbon capture technologies that say, well, maybe we can engineer a process and not wait for a plant to breathe it in. We can just engineer a process where the chemistry is such that the carbon dioxide will automatically get reabsorbed from the atmosphere. And I'll talk about that in a little bit. But each of these, right? And you see I draw a little green line out there. And along with purchasing renewable energy credits. And that's purchasing renewable energy credits is like Audra has solar panels at home, right? So she's generating a certain amount of renewable energy. And I say, and I am burning coal in my basement. But I go and say, hey, Audra, I'm feeling really bad because I'm looking like my impact is really high. But what if I give you some money and I buy some of the, big, and kind of like take credit for what you're doing with your renewable energy? Then I can probably take that off my, my accounting. So there are ways you can say that, well, I am not, my energy sources are not very clean. However, I am actually giving money to somebody and helping them subsidize, create more renewable energy. And so there is some of that credit I should get to offset where my impacts are high. So I put a little green line there because some of these methods can be essentially, well, let's throw money at it solutions, right? And I'm guilty as charged because you can find ways to sequester, to offset your own personal carbon footprint, right? And there are companies out there that do it. And I found that because I tend to fly quite a bit, I have found that I can actually throw a little bit of money at it every month. And I actually found the company's called TerraPass. They do a great job. This is not an advertisement for them. They do a great job. But what they do is they take the money and invest it in different kinds of renewable energy projects across the country. And you end up being able to look at their portfolios, and they're doing some really good work. So I said, well, I don't have to feel so guilty about all my flying emissions because I'm trying to offset that. And so this is the idea of offsetting, right? And clearly, as we can see, the idea of offsetting, so EPA right now in their guidelines that they're coming up with, they're not very, very warm on the idea of offsetting. So, but at the same time, a lot of organizations are thinking about using offsets. Carbon capture technologies, this is turning into $1 trillion market, if not more, okay? Because there are many entrants in this market, and actually some of the stuff I've been doing here since I came to FHWA on sabbatical is actually looking at some of these technologies, particularly in the area of pavements and construction materials, right? So the biggest picture, the blue picture I have out here is from ExxonMobil, right? ExxonMobil, they have come up with this quote unquote bold plan to capture and store carbon. And what you're seeing out here, the schematic, I felt the best thing to do was to just reproduce the schematic as is, which is they literally are capturing carbon dioxide out of the atmosphere and burying it under the ground. So under the Gulf, right? At a depth of thousands of feet under the seafloor, right? Literally sequestering, right? Then there is a carbon cure technology, and I need to do more. I need to do more learning on it myself, in the sense that we're still waiting for them to publish their results. But they're talking about creating concrete and pumping carbon into concrete as the concrete is being cured, and by doing that, the concrete is capturing all that carbon that it then keeps and holds on to for however long that particular infrastructure lasts. And as we know, with infrastructure, that's a fairly long period of time. Then there is another company that I was reading about, and there are quite a few the carb fakes that they're looking at turning carbon dioxide into stone. This is a very interesting market. A lot of these technologies are new. They're not perfect. They're still working on making them better, but there is definitely a lot of scope for growth here as time passes, right? But
just
again,
a time check. We have about 15 minutes.
Yeah, and I've got about a couple more slides.
Yeah, there's some questions.
Yeah, and I need to stop talking. So Heather insisted on me putting the slide in this morning. She was like, "No, Amlan, you got to put that slide in." So I did. So what do Heather and I? We've been having, as I said, we've had a lot of fun these last few years. What do we do? Well, part of what we do is we model and learn about highways, construction processes, and then we can make sure the underlying data is good, because all this accounting depends on a lot of data sets, like what is the impact of energy for our electricity production in the United States. That took us about 2.5 years to make sure we had the right data to use, regionalized appropriately. Turn that into practice protocols, and then all of that goes in informing policy. And the LCA PAVE, that little tool that you're seeing at the bottom of the page, that is a tool that we've worked on together. And then some of the FHWA, of course, I've worked for, and Minnesota Department of Transportation, as well as Caltrans. I've been involved in projects with them.
And one question, Amlan, was what phase for material products has the largest CO2? So if you could, life cycle phase or.
Yeah, well, so the question is, for a material, if you're just talking about the material itself, you have to talk about what system the material is going into. So if you're talking about pavement systems, it's the use stage that has the highest impact, right? It's about, depending on what the nature of your infrastructure is, you're looking at between 85% to 90%, right? But there is a lot of low-hanging fruit in that 12 to 15%, which is after the production and construction of that particular asset, where significant gains can still be made at this time. And then this is, Heather had mentioned, we've already mentioned this a couple of times. By the way, that picture is a picture I took on site last week, right? And I'm also involved with a fair amount of, my background is in construction, so I'm involved in a lot of, asphalt as well as concrete paving, and enjoy every minute on site. And that's like an asphalt paver out there. So you have to think in terms of the energy that goes in there, as well as the asphalt mat as it's being put down. What is the life cycle, the cradle to gate, the life cycle emissions of that particular material, and then how do you manage that over the life cycle, over the use stage of that particular pavement, right? So with that, the one before I turn this to conversation to everybody else is there is a component of this which is the social equity, right? So when we say let's go ahead and reforest half the planet, well, we're probably not going to be reforesting downtown Manhattan, right? Probably not, right? So where are we going to be reforesting? And it's likely, and we've had these kinds of engineering decisions made earlier, where the easiest place to go and reforest is probably going to be a poorer part of the world, where we run the risk of buying up land that could be used for food production. So a concern out here is that as we decide to do our different ways of offsetting our emissions, reforestation, or start growing corn, and we've already had this experience with biofuels, the first generation biofuels, where we start growing corn, a food source, for an energy source instead, right? And what impacts that has on food markets, and who does that impact the most, right? So this burden of these exercises we have to have a discussion on that, and there is a significant discussion around what the social aspects of that are. And with that, before I'm going to turn this off to you guys and say, well, what can we do? What can you and I do? Now I know Alan Turnquist, our new I'm going to get his position wrong, but our new big sustainability honcho at Michigan Tech, he's here. And I know Michigan Tech is doing some pretty cool things with trying to figure out ways to first estimate where are we, what is our benchmark, what is the benchmark of our emissions and energy use, and then figure out ways to not just reduce that, but potentially get to net zero in the future as well. And with that, I guess the questions are all
right. Well, thank you, Amlan. So there's maybe maybe I'm going to kind of cherry pick a couple of these because I think in some ways you've answered a couple of them. I think there's one I'm not sure you're going to know the answer to because it's not exactly your area of expertise. You were just talking about here's what ExxonMobil is doing. So the question is,
Right.
what are the long-term environmental consequences of storing CO2 underground?
This is a very, very interdisciplinary field. As I said, I'm a construction engineer. I work primarily in applying a lot of these, the underlying science to the area of construction materials. But I mean, I'm looking at some of these questions, and honestly, I cannot answer these questions. And as I said, when we work in these fields, we're constantly working with experts from other fields. So I think there is a question on geology in there. There is a question. I think there is a deeper question on climate change out there, and some of these questions, when we're dealing with these very complex problems, we end up trusting our colleagues and their expertise, and they trust our expertise, and that's how we kind of work together and move together. So I think there was a question earlier about looking at the natural earth changes. Well, again, if you push me hard on that, I will not be able to answer that question with the level of detail as I would say about an asphalt mixture design. However, I can, and the literature is out there, and the appropriate sources and the reliable appropriate sources are out there to read from, and there is some humility in how we work across these different fields and recognize that we're dealing with a fairly big problem, and so we have to trust each other and work with each other on some of these solutions.
That's one of the things I was going to say that I like the most is LCA or sustainability breaks down silos. You work with so many different disciplines. You work together with colleagues from EPA, you work with chemical engineers, you work with construction manufacturers, materials, so it's not, we have to use each other's expertise and break down the silos that were created. I guess I saw, it was an old story of the pyramids. The pyramids were designed, one of the great engineering, by one person. They knew all these different trades, and then engineering just spread out into many different specialties and disciplines, and which is good too, because it allowed us to niche in. Now we need to break down the barriers of our disciplines and come back together for the next discoveries.
So Heather, there are a few questions I want to address here. I think there is a question from Daryl here. Mm-hmm. And even if net zero emissions is achievable, if nothing is being done to reduce the much more significant gases as methane and water vapor, how are we significantly reducing warming? And that's a very good question, because it harps back to the point I was making, that when we're talking about emissions, we're talking about carbon dioxide equivalent. So yes, we are also counting the methane. Definitely the methane, right? And then there are a couple of other questions here that I can actually answer. What is the old asphalt pavements that has been replaced could use asphalt that has been absolutely. So when we are building, asphalt is almost 100% recycled, right? And so there is in fact, when you're looking at a pavement that is being reconstructed, sometimes you could do a hot in place repaving. And that is sometimes, even though it's a very energy intensive operation, it turns out to be, because you're recycling so much of that pavement, it turns out to be a better choice sometimes than using fresh asphalt, milling off the surface and filling it with a fresh asphalt. And we just recently completed a study for Arizona DOT looking at that. And so, yeah, absolutely, we're recycling asphalt, and we should be doing more of that. Absolutely.
So Amlan, getting back to what you're talking about, it's looking at the entire life cycle of that material, right? And comparing it to another material's life cycle when you go back to it having to be transported, processed to get to being a road.
Right. There is another question. Well, how do you calculate this stuff? And I'm answering that very simply by saying life cycle assessment methods, but that's a full-blown graduate class. I don't think I can quite answer that fully here. But if I teach that class in future, please, you're more than welcome to jump in. Cold climates, absolutely. In cold climates, it seems like roads are constantly being ripped up and repaved. What is the average time frame a road is designed for? That's depending on who you ask, we can get into a good fight on what that time period is. So if you construct an asphalt pavement well, you shouldn't have to touch it for the first 8 to 9 years. right? If you construct a concrete pavement well, depending on what the nature of the, whether it's continuously reinforced or not, what kind of reinforcement you're using, you shouldn't have to touch it for 12 to 15 years. But does that always happen? Not necessarily. So, and there are big databases out there that people study and try to answer that question, and they do the modeling in the lab. And so, yeah, that's a field by itself. There's another question that I cannot answer. What is the net decrease in generation efficiency when carbon capture? Dr. David Schonard, I know he is going to be talking on this forum in a couple of weeks, I think, and that's right down his path, right? Large potential for nuclear power has not been included in. Actually, that's kind of interesting because I did not intentionally use nuclear power for this discussion, but nuclear power, all the methods that we use account for nuclear, the materials, the nuclear materials, the fission materials that are used. And so all our methods account for nuclear power as well when it is used, right? And we can have a conversation about nuclear power offline on this, but that's, again, another can of worms with lots of engineering concerns as well as social considerations, for sure.
There's a question here. Do you know which renewable energy source has the cleanest LCA? Considering everything that needs to be mined, manufactured. And who I was thinking, Amlan, is our colleagues in the Fed Commons. They do a lot of LCA to direct and advise the federal agencies on what energy sources to pursue.
Sorry, Heather.
I was just to say, they are looking into it. I don't know the answer.
I would, based on what I've said, I'm going to go on a limb here, and I know this is going to be on YouTube, so I'll probably get murdered for this. But I'm going to go on a limb and say it's hydro. I think hydro is probably our best, in terms of looking at the impacts. It's one of our lowest impacts. But
I know that Brazil has one of the largest. They use the most hydro. They have the most renewable energy grids because they have a huge hydro.
Yeah.
Let's see if we've got any more. Or go ahead, Audra.
Oh, no, go ahead.
Let's see if.
Maybe will the construction equipment ever be electric powered? What do you think?
Yes, why not? See, that was another can of worms I did not want to open today. But, with electrification, electric vehicles, a couple of weeks ago, we had our LCA conference, and there was a discussion on whether our power grids are absolutely fully prepared to, like, if tomorrow morning the entire fleet went to electric, would we be able to handle it? And depending on which state you're in, some states can and some states can't. And then also the question, that's worth thinking about is, well, if you're driving an electric vehicle, if you're driving a Ford F-150 as an electric vehicle versus if you're driving one of those tiny little Fiats on an electric vehicle, the impacts are different. And sometimes you could be driving a gas, ICE combustion engine, internal combustion engine vehicle. That's a smaller one that is probably better than an electric vehicle that has a much higher energy demand. So again, those discussions come in. Now with construction equipments, it's not a personal vehicle fleet, but they're also very they have to be energy efficient, and they're also very energy intensive. So those discussions, but I am aware of construction equipment, of people who are studying electric options for construction equipment as well.
And I would add, they're looking at automating construction, paving, and some of the procedures that are in place that we can, as well as what I think is really cool is there is a project being done where they're looking at paving, charging your electric vehicles, the batteries, so that are in the electric type of vehicles. So I don't know how that technology works, but something that they're putting into the pavement, and it can charge the vehicles while they're driving over on top. Something similar, I think, to how rail technologies work. So there is, these new technologies are definitely probably going to impact the construction, pavement, how we design. All these recycling questions all come into play. So there's huge challenges in the future. It's exciting.
Yep. And if you want to get, Audra, you should be doing this. Do the little pitch for come to Michigan Tech, and we have a lot of fun working on this stuff.
We do. And so I
Yeah.
think Amlan, why don't you talk about John's question? He asked, do Michigan Tech students pursuing civil engineering degrees take many material engineering courses so they may better understand the life cycle aspects of materials? What should high school students study to best prepare for Michigan Tech? And we can tag team that, but maybe do you want to talk about the first one?
Oh, absolutely. And this goes to what Heather was mentioning. I mean, at this point, the engineering curriculum that I graduated with more than 20 years ago is no more the curriculum that we would like our students to have and teach right now. So yes, there is, if you're working in life cycle assessment, you can get life cycle assessment expertise out of chemical engineering, out of civil engineering, out of mechanical engineering. And so like we have a little coterie of faculty across these different disciplines who work in life cycle assessment. We speak the same language, but we deal with different domains. Understanding materials, I kind of was not interested in materials at all when I was in college. I thought it was like not my area of interest. As it turns out, I've had to learn a lot about materials over my professional life. So yes, so there is also the lifelong learning component to that. But yes, in our civil engineering program, we have the options to get more grounded in asphalt materials, concrete chemistry. Those two materials definitely play a major construction materials. Wood, of course. So and Audra, I'm probably missing some of the class there, but wood, steel, of course, wood, steel, concrete, asphalt. Wood, steel, concrete, asphalt, right? There are 4 of them. We definitely place a lot of emphasis on understanding the material aspects of it. And understanding how these materials are responding. Like steel, for example, pretty much everything that is being manufactured in the steel industry right now is being manufactured for second, third uses, right? So after your first use, the material can be recycled into a second use, and that's how the material is being designed. So yes, absolutely. Much of these are part of the curriculum, and they're electives. So there is no reason why somebody can't go and take a class in chemical engineering if they want to get more depth in a particular area, or mechanical engineering, depending on the nature of the topic.
And we do that. So for instance, in the civil engineering curriculum, it's a 1,000 course, and Amlan has been a guest presenter where he talked about green roads. So we introduce students to some of the frameworks that might enable them to make decisions as a civil engineer when they are doing projects, whether that's LEED, Envision, green roads, so they can be thinking about sustainability or reducing their impacts as the designer. So that kind of comes along with their technical background. Maybe one last question, and then we'll go, because I just can't help it. And it's the only question I think we've really had about social equity, since you brought that up, Amlan, is that along with social equity concerns, are there other practical issues related to reforestation, such as a viable solution? For example, trees becoming carbon sources or sinks in the absence of sustainable harvest, funding for long-term maintenance, or other issues? It was Michelle's question, if you're scrolling around, but since it's one of the few that asked about social equity concerns, I thought that might be nice to answer.
Yeah, this is definitely this is a tough question too, because again, this is a tough question. I will not pretend to be able to give a simple answer to this, because one of the things that we have to start thinking about is the feedstocks, right? So what happens to the feedstocks if what is happening to those forests? How long are they? How long will they be harvested, and if they do, what happens to them, and how are they being used at that point? And this is funding for long-term maintenance, other issues. Yeah, this is definitely a forestry issue. This is definitely a forestry question. So looking at these, and this is on a more broader topic, related topic, is that when we're looking at these biogenic materials, where we're saying, oh, look, it's capturing all this carbon dioxide. Well, then we also have to think about what happens to that feedstock. The carbon dioxide is going in, but will this be used as a source of fuel in the next, well, if it's getting used as a source of fuel in the next 10 years, then was that capture actually really worth it? Or is it being trapped, is the carbon being trapped in for a period of like 100 years or 150 years? So that time period also becomes important. So in the case of reforestation and what happens to those forests, or what the fate of those forests are, that is definitely a question for forest management, absolutely. It's a great question that apparently I'm not giving you a very satisfactory answer for.
But I think what you're talking about is the complexity of these issues that we need to work together and solve. And you and Heather highlighted that repeatedly throughout the presentation. And I think the key word is net. And you did that nicely online. You talked about the sources, you talked about sinks, and you talked about how to offset to actually get there. It doesn't mean zero, it just means net. And that net word is really important. So it is the hour. We never can get all to the wonderful questions that are asked by this group, but we really appreciate you all asking them, for the great discussion. Amlan and Heather, thank you so much for your time tonight. Great job. And to all of those out there, thank you. And we will see you next week here on Husky Bites. Thanks and good night.
you.
Thank you.